We are going to start this course with Chapter 8 from your Physics Intermediate textbook. Let us start by discussing briefly the important phenomenon of light. We can consider light as a form of energy that stimulates our sense of vision. In fact, you may remember that light is actually a wave. It forms the visible part of the electromagnetic spectrum. We are able to see objects whenever light reaches our eyes, either by being emitted by a source, for instance the sun or a lamp, or by being reflected off objects such as a person or a tree. We represent light traveling from one point to another using rays. The direction of a ray indicates the direction of travel of light, also called the direction of light propagation. When light is incident upon a surface, it may be partly reflected, partly absorbed, and partly transmitted. Transmitted meaning allowed to pass through, which is only possible for transparent media. Substances that do not transmit any light are called opaque. In other words, no light is allowed to pass through. This figure shows what happens to a ray of light that is incident upon a very good reflecting surface, such as a mirror. The laws of reflection state that the incident ray, reflected ray, and normal to the surface all lie within the same plane. In other words, all lie within the same two-dimensional space. So if we look back at the figure, we are saying that the incident ray, reflected ray, and the normal to the surface, these should all lie within the same two-dimensional space. Secondly, the angle of incidence, here denoted by I, is equal to the angle of reflection. These laws have all been proven experimentally. Now, in the case of transparent media, such as light passing from air into glass or water, a different phenomenon is observed, which is called refraction. This phenomenon is very easily observed by, say, placing a pen in a glass full of water. Refraction occurs due to the fact that when light enters a different medium, it undergoes a change in speed. Its frequency remains the same, whereas the wavelength changes. So light entering a different medium, we're saying that it undergoes a change in speed, where the frequency remains constant and the wavelength changes. If its speed decreases, then it bends towards the normal, such as shown in this figure for light traveling from air into water. So we have bending towards the normal. On the other hand, if the speed of light increases, such as shown here for light traveling from water towards air, then bending occurs away from the normal. And here are the laws of refraction. The first part is similar to what we had for reflection, where the incident ray, refracted ray, and normal to the surface all lie within the same plane. The second part is called Snell's law, and it states that the sine of the angle of incidence is proportional to the sine of the angle of refraction. So sine theta 1 is proportional to sine theta 2. In equation form, the constant of proportionality is called the refractive index of medium 2 with respect to medium 1. Its symbol is the Greek letter eta with subscripts 2 and 1 indicating the respective medium. So eta 2, 1 represents the refractive index of medium 2 with respect to medium 1, and it is equal to the ratio of the sine of the angle of incidence to the sine of the angle of refraction. So we define eta to 1, so the refractive index of medium 2 with respect to medium 1 is defined as the ratio of the speed of light in medium 1, we're calling it V1, to its speed in medium 2, V2. So we're saying that eta to 1 is equal to V1 on V2, ratio of speeds. Note that the refractive index is hence a dimensionless quantity, meaning that it has no units. Meters per second in the numerator cancel with meter per second in the denominator, leaving us with no units. We can also define the absolute refractive index of a medium. So when we say absolute refractive index eta of a medium is defined as the ratio of the speed of light in vacuum or air, because these are approximately the same, to its speed in that medium. So mathematically, we're saying that eta 1, which is the absolute refractive index of medium 1, is equal to C. It's the symbol representing the speed of light in vacuum, 3 times 10 to the power of 8 meters per second, divided by the speed of light in that medium, here denoted by V1. And similarly, eta 2, which is the absolute refractive index of medium 2, is equal to speed of light in vacuum, C, divided by the speed of light in that medium, V2. So these results follow by the definition of absolute refractive index, which we have just stated. By these results, if we had to divide eta 2 by eta 1, we substitute accordingly, then we have C on V2 in the numerator from here, C on V1 in the denominator from here. So the speed of light in vacuum, C, cancels, and we are left with V1 on V2, which we have just seen that it is equivalent to eta 2, 1. So in other words, we are saying that we can express the refractive index of medium 2 with respect to medium 1 in terms of the absolute refractive indices of both media. So we are saying that the refractive index of medium 2 with respect to medium 1 is equal to the absolute refractive index of medium 2 divided by the absolute refractive index of medium 1. But we have seen that this is also equal to sine theta 1 divided by sine theta 2. Let me show you again the result. It was here. Okay, so I'm quoting this ratio of sines. And we have also seen from here that it is equal to V1 on V2. All right, so we have different ways of expressing this result. And moreover, since we know that V1 is F times lambda 1, you should remember the equation V equals F lambda, where F represents frequency and lambda represents the wavelength. So we can substitute F lambda 1 in the numerator and F lambda 2 in the denominator, the frequency being the same. Okay, so we have just said that when light refracts, its frequency remains constant, so the frequency remains the same, so it cancels. We have different wavelengths, lambda 1, lambda 2, which means wavelength in medium 1 divided by wavelength in medium 2, and here we have another result. So any of these you can use in the questions according to the information given and what you are asked to calculate. One particular form of this equation is the one shown here in the dotted yellow circle and is rearranged in this equation in this form such that we have the refractive index of medium 1, eta 1, multiplied by sine the angle of incidence, sine theta 1, which is equal to eta 2 sine theta 2. So on the one side we have the properties of medium 1, on the other side the properties of medium 2. And this is a very useful way to handle questions on this topic. By the definition of absolute refractive index, we find that eta should always be greater or equal to 1. Okay, so it follows that the absolute refractive index, being defined as the ratio of the speed of light in vacuum to the ratio of the speed of light in a particular medium, then it turns out that the denominator, which is the speed of light in the medium, can never exceed that of vacuum. So we get a ratio that is always greater or equal to 1. In practical terms, the refractive index simply gives the factor by how much light slows down when it enters that medium. So the higher is the refractive index of a medium, the slower light travels in that medium and the more it bends towards the normal. For example, if we're given that the refractive index of glass is 1.5, then this simply means that as light travels from air into glass, its speed decreases from 3 times 10 to the power of 8 meters per second to 2 times 10 to the 8 meters per second, found by dividing the speed of light in air by the refractive index of glass, 1.5. Obviously, the refractive index of air results to be approximately equal to 1. And this is because it is found by dividing the speed of light in vacuum by the speed of light in air, which is approximately the same. So we get equal numerator and denominator giving approximately 1. Okay, so you should be aware of this because in problems it is taken for granted that you know that the refractive index of air is approximately equal to 1. Now here we have a simple situation where light is traveling from medium 1, here representing some type of transparent plastic, into medium 2, which is glass. So from the diagram, the fact that the light ray is bending towards the normal shows that upon entering medium 2, it is slowing down. So we say that medium 2, which in this case is glass, is, this is a very important term, optically denser than medium 1. The question is telling us that the angle of incidence is 30 degrees, the angle of refraction is unknown, we are given the speeds in medium 1, the plastic, and in medium 2, glass, and we are asked to calculate the absolute refractive indices of plastic, eta 1, and glass, eta 2, the refractive index of glass with respect to plastic, eta 2, 1, and the angle of refraction, theta 2. We've been saying that a refracted light ray is one that slows down upon entering an optically denser medium, meaning a medium having a larger refractive index, and consequently it is deviated. That is, the light ray changes direction by bending towards the normal in this case. We can calculate the angle of deviation by finding the difference between the angle of incidence and the angle of refraction. The angle of deviation is simply the angle through which light has changed its course. So, in this case, the angle of deviation is 9 degrees. Something useful to keep in mind regarding the behavior of light is the principle of reversibility, which states that the paths of light are reversible. This means that if a light ray is incident, say at 35 degrees at an air-water boundary, producing an angle of refraction of 26 degrees, then had light been traveling the other way around instead, that is, from water to air with an angle of incidence of 26 degrees, then the angle of refraction in air would have been 35 degrees. In other words, the light ray simply travels along its original path in the reverse direction.